Hello everyone, we will be presenting our work sketched on the flops towards efficient networks for human sketch acceptance CVPR 2025. Despite great progress in sketch-based applications, the efficiency of such applications remain largely underexplored. Primarily, the existing networks are large and do not aim for efficiency as they rely on high-resolution sketch images. On the other hand, conventional efficient networks are designed for photos and do not cater to sketches, resulting in lower task-level accuracy. Thus, our goal is to design an efficient network for sketch applications to ensure limited computations without compromising the task level performance. So, the principal challenges are designing sketch specific efficient models and optimizing performance and efficiency. We understand that sketches are sparse and abstract, yet highly expressive. The high expressiveness on one hand controls the information content, while the abstract and sparse nature of sketches provide an avenue for compressing the information. Based on this understanding, we propose a two-way approach. Firstly, we aim to transfer the task level performance from better models to efficient ones. Secondly, our approach targets the resolution of sketch images due to the unique sparse nature of sketches. Before going to our architecture, let us take a look into a pilot study to verify our intuition. We try to investigate the information loss when scaling sketch image resolution considering the fine-grained image retrieval task. In particular, we asked the sparse nature of sketches help in retaining information contained in the sketch when decreasing the resolution. Comparing the fine-grained image-based image retrieval or FGIBIR and fine-grained sketch-based image retrieval or FGSBIR, we observed the following. Photos are pixel dense and extremely vulnerable to information loss when image resolution is limited. We see a rapid accuracy drop when query image is scaled down. On the flip side, sketches are sparse and abstract. Expressed with a few strokes, sketches prove to be more tolerant to input size scaling compared to photos. Our pilot study also reveals that only a few query sketches really require high resolution. A vast majority of query sketches can retrieve corresponding photos at a low resolution, and progressively, fewer and fewer query sketches remain unsuccessful, requiring a higher input size. Based on this, we propose a two-stage solution. Firstly, an adaptive canvas selector can be employed to predict the appropriate input size for the query sketch. The sketch rendered in the predicted canvas size can be used for retrieval using an efficient network trained using a task level knowledge from a large state-of-the-art model. Before getting into the architectural details, we establish a state-of-the-art FGSBIR model with VG16 backbone as the pre-trained baseline as an essential element of our framework. The first stage of our two-stage pipeline, SketchNet V1, uses a small and efficient backbone MobileNet V2, trained with a knowledge distillation strategy. It is trained with the supervision of conventional sketch photo triplet loss, trying to bring the sketch representation closer to the representation of the matching photo and distancing from the same of a non-matching one. For the knowledge distillation, we focus on relative knowledge embedded in the sketch photo triplet alignment in the representation space of the pre-trained baseline. Particularly, the L2 distance between a pair of sketch and photo representations is distilled from the pre-trained teacher model to the efficient student model using a Hoover loss. L2 distances between each individual pair of the triplet sketch positive photo, sketch negative photo, and positive photo, negative photo are considered separately as an alignment between the triplet, employing a smooth L1 loss from the pre-trained teacher embedding space to the student embedding space. The total loss consists of these two components, supervised triplet loss and the knowledge distillation loss, and their contributions are controlled by the hyperparameter lambda. This entire setup is trained with query sketches rendered in varying canvas sizes, and the loss is expressed as the mean of all the versions of the triplet with different canvas sizes for the query sketch. The next stage of our framework involves SketchNet V2 that uses a sequential model like GRU or LSTM as an adaptive canvas size selector, trying to predict the correct canvas size for any sketch from the stroke level representation of the sketch using as few strokes as possible. The SketchNet V1, the efficient student network we trained, is frozen and acts as a critic for the training process. The sequence model realizes a policy network followed by a linear layer modeling the probability of the choice of discrete canvas sizes from a predetermined set. The training employs a reinforcement learning framework where canvas sizes are sampled from the categorical distribution of the predetermined set. Next, we design the reward function. One of the components of the reward directly depends on the computations. We determine a loss term based on the network predictive probabilities across all the canvas sizes and pre-calculated flops of SketchNet V1 for the corresponding canvas sizes. The reward is computed as the negative of the loss term. The intuition is simple. More flops should lead to less reward. Next, we look at the other crucial component of the reward, the retrieval accuracy and loss. We use the inverse of SBIR inference retrieval rank and negative loss computed using SketchNet V1 scaled by two hyperparameters. This helps SketchNet V2 prioritizing retrieval accuracy. Both of these components contribute towards the total reward controlled by a hyperparameter lambda f. The entire setup is trained using a policy gradient optimization. We evaluate our framework on two FGSBIR datasets, SuV2 and ChairV2, along with a categorical SBIR dataset, Sketchy Extended, and a single-level SBIR dataset, FS Coco. We choose a few state-of-the-art FGSBIR frameworks as competitors. For baselines, we choose a few state-of-the-art knowledge distillation strategies applied in our context involving the student backbone MobileNet V2. We also take the VG16 backbone and use a model compression technique pruning, establishing a few more baselines. And we compare it with a simple triplet network in conjunction of SketchNet V2. We use a top Q accuracy metric to measure task level performance and average flux count for computational efficiency. Here we incorporate the competitors in the proposed framework. We see our framework reduces the flux greatly compared to others with an insignificant reduction in top 1 and top 10 accuracies. Taking a closer look at the empirical data, we observe abstract sketches with less details can easily be rendered at a lower resolution without much of information loss. Next, we look at the impact of canvas sketch on the performance efficiency trade-off. Recall that we had a control hyperparameter lambda f in the reward function. This hyperparameter gives us a trade-off between flops and accuracy and can be tuned for optimal performance according to the requirements. We also perform several elaborative studies to justify our design choices. We perform a reward strip-down analysis and observe that each component of the reward function is crucial for optimal efficiency and performance. We perform an ablation on different small networks as backbone for SketchNet V1 and found our choice of MobileNet V2 to be the best. Next, we ablate on different sketch encoders for SketchNet V2, including LSTM transformers and an image-based encoder. We see our choice of encoder GRU has the least flops with at-per performance at the task level. We performed some additional studies. We compared the accuracies and flops for the state-of-the-art FGSBIR models with different canvas sizes and see a first drop in accuracy with lowering query sketch resolution. We also performed a detailed study on the backbones and see VG16 as feature and MobileNet V2 as student result in both least flops and the highest accuracy. Thanks for your attention.